Hi, my name is Brian. I'm the Department Chair of Mathematics at Okanagan College. And today we're going to talk a little bit about RSA encryption, and we're going to take a look at a specific numerical example, kind of tie it to how we might use some of this theory from modular arithmetic to encode some messages. So let's get to it. So the RSA encryption system was actually described in 1977, and the individuals involved were called Ron, I love this guy's name, Ron Rivest. We had Adi Shamir. And we had Leonard. Not Leonard 317, we had Leonard Adelman. Leo? Wrong Leo. They described their RSA crypto system. And I think it's cool. So what they did was they basically said, okay, let's take the first letters of our last names, we'll combine them all together, and that's going to give us RSA. So this system is described by these folks, and all three of them get credit for the letters that we use for this system. So what is the premise? So we saw with the Diffie-Hellman key exchange, the premise was that it was really hard to solve modular power problems when we were working with large prime numbers. The premise for RSA is slightly different, but we're still going to be using some of the tools that we saw in that modular arithmetic section, which is pretty cool. So a premise here, kind of how it works is the client is going to request information. And we'll give away what's known as the public key. So the client's actually going to have both the public key as well as their own private key, but they're going to give part of that information away. In this particular algorithm, they're going to give that public key away when they go to make the request. The server is going to use the public key to do the encryption. And then they're going to send that information back to the client. And once the client has that information, they use their kind of personal private key to unlock that information and read it. So if you want to draw a really lovely artistic rendition of what RSA is going to look like, we have something that looks like this. We have our client. So that's like you or I. And we have access to both the public key, which for the sake of the last couple chapters, we've just been denoting that as an unlocked lock in this particular case. And we have a private key.
Have you ever?
So we have our client that has the public key and the private key. The client is going to request information. So the client is going to go ahead and send the public key. So this public key is going to get sent to the server, which I'll just pretend looks like a computer. That's what a computer looks like, right? There's our beautiful computer. Right, so now the computer is going to have the public key. And then what's going to happen is that server, in conjunction with the public key, is going to encode the message. So how do I want to write this? Maybe let's loop back to the client, because really what's going to happen is, things are going to get looped back to here. And along the way, the data is going to get encrypted, right? So our message or our data, whatever we want to share between the client and the server, is going to get encrypted. And so I'm going to denote that by this lock actually locking. Okay, so this information gets sent to the server says, boop, passes it back to the client, and the client now has the key that can open up that lock. It's the private key. So kind of the last step here, let me just maybe pop this back to green, is now, hello, green, thank you. Now the private key is going to act on that encrypted information, and we're going to be able to unlock that. So it's going to feel a little different than the Diffie-Hellman key exchange because there's only one individual here, right? There's one individual that has a public and a private key, and they're requesting information from a server. Whereas the Diffie-Hellman key exchange was more so between two people. So it was two individuals that wanted to share information, but they had to do it through a public, like a public-facing connection, right? So the only way for them to do that reasonably was to kind of utilize some of this weird mathematics in the background to do it. Okay, so that's kind of the general picture of how the flow of things works through the RSA algorithm. Let's actually do a numerical example. So I'm just going to go ahead, I'm going to work through the steps with you so you can see some of the mathematics and how some of that works. So step number one is our key generation. So a little bit different compared to Diffie-Hellman. What we're going to do in this case is we are going to choose two large prime numbers, but rather than creating a function that connects those two prime numbers together, we are going to multiply our two prime numbers, and then we're going to use the Euler phi function to do some work for us. So the difficulty, I guess, of cracking or kind of decrypting the RSA algorithm lies in the fact that it's really hard to factor a really, really large number. There are some ways to do it, and you would learn that in a typical, probably cryptography class. But for the sake of, what we're talking about today, let's just assume that it's really hard to factor big numbers. So to start, we're going to just select two really large prime numbers. So what's going on with these prime numbers? We need them to be random. And we need them to be far enough away as well. I hope I have some notes about why that might be true. It's not obvious to me why we would need that large difference between them, but my guess is there's probably an algorithm for checking for factoring big numbers where primes are close to each other. There's probably some kind of algorithm that would help us easily decipher the RSA algorithm if these prime numbers were relatively close to each other. So I don't know. I'd have to read a little bit more. I don't know exactly how big that difference has to be. And I'm not exactly sure why they require this, but I suspect that the large difference is needed in order to ensure the safety of the algorithm. And of course, we're not going to share these prime numbers with anybody. If we were to accidentally share these numbers with somebody, they would be able to decipher our algorithm super fast. Because the large composite number that we're creating is just a product of these two prime numbers, as you're going to see. So we really want to keep these prime numbers secret. So once we've selected our two large prime numbers, the next thing we want to do is multiply them together to get a really, really large integer n. Once we have that really large number n, we're going to calculate phi of n, which is relatively quick to do because this is a composite number. It's just composed of two prime numbers, so we have a really nice formula for calculating phi of n. Once we have phi of n, we're going to select a number that is co-prime to phi of n. And then the last step to get everything initialized is to find the inverse of that co-prime number that we've selected. And that becomes our private key. And we'll take a look at, once we start working through some of the theory and some of the example here, about why this works the way that it does. It's actually a really cool little kind of sneaky way to make things work. Very, very clever way of doing this. Okay, so let's start kind of visualizing what this looks like in a picture. Basically, we're going to start with P and Q. Okay, so these are our kind of random prime numbers. We are going to go ahead and multiply those numbers together to get a really, really big integer.
X!
Thanks, Fanny, for the distractions. So this n is actually the mod that we work with as well. Really big. It's a really big mod. It's huge. Some might say very long. Once we have n, then we can calculate Euler phi of n. So Euler phi of n is just p minus 1 times q minus 1. That's our formula when we're working with prime numbers to calculate the number of numbers that are co-prime with n. And what do I want to note here? I missed a little bit of information here from my notes that I do want to add. So this n is actually going to be the mod that we work with when we're encrypting and decrypting. And then phi of n is going to be the mod base that we're going to be working in when we're working with this coprime number. So the next step is to find a coprime number with phi of n. We're selecting a coprime number so that we can find an inverse, mod phi of n. So I just want to kind of jot down some of that. So this is the mod we're going to work with when finding the private key. And again, it's maybe not obvious right now why we have these two different bases that we're working with. I'm hoping I'll be able to tie that together a little bit later. Okay, so once we have phi of n and we know what that value is, our next step is to find a coprime number with phi of n. So the coprime number, we're going to call that E. And we're explicitly going to pick it so that it lands somewhere in between 1 and phi of n. So in other words, we don't want to pick the identity element of the group, and we don't want to, phi of n is also the identity element of the group. So the idea here is we're going to pick one of the congruence classes that's in between the identity and our largest element. Okay, so the only restriction we need here is we need the GCD of phi of n and E to be 1. So that's the only restriction that we have on E here. And then our last step is to calculate the inverse of this, and we can do that using the Euclidean algorithm. So I'm just going to zoom out so you can kind of see the process here. Start with your random primes, multiply them together, calculate phi of n, find a number that's coprime with phi of n, find the inverse of that. Once you've done those steps, then you have both the public key and the private key. So let's put it all together here. In our final step, with the information that we now have both n and E, which makes up our public key. And we have N and D, which make up our private key. Okay, so again, what do we mean by public and private? Public is the one that we're allowed to share. Private is the one that we keep to ourselves. And what's the importance about this value D that we're calculating? Well, it's going to help us decode everything, so that's why it's called D. The public key is the one we're allowed to share. And it's the one that's going to help us encode. So E helps us encode whatever we're working with. So there we go. And that's kind of the setup and the initialization phase for how we get both the public and the private key. Let's pop into a numerical example so you can kind of see what that process looks like. Because there's a lot of stuff happening here, right? Okay, we're going to pick ridiculously small prime numbers and multiply them together, because that's how we roll. So let's suppose that we have two prime numbers. Let's take 61 and 53. Terrible choices for prime numbers. They're way too small. They're probably way too close together as well. So it would be very easy for somebody to come through and just kind of guess and check and decode whatever we're hoping to work with here. So terrible choice. We want these to be far bigger than 2 digits long. We'd want it to be really big prime numbers. All right, so next step here is to calculate n. We're going to calculate n by multiplying p and q together. which is 3,233. And then we're going to go ahead and calculate phi of 3,233, which should be p minus 1 times q minus 1. So it's going to be 61 minus 1 times 53 minus 1, or 60 times 52, which is 3,120. So next what we would naturally do is try to find something that's co-prime to this particular number, 3,120. I believe this is done at random. So I guess the idea here would be maybe we'll select at random, we'll go through some computations to make sure it has an inverse. All we're really doing is just double checking to make sure it's co-prime, I guess, with 3,120. As long as it's co-prime with phi of n, we know that we can find an inverse inside that group that we're working with. I think 17 should be fine. 60 has what? 30, so 60 is like 30 times 2, so there's a 15 in there. So 60 has 3s, 5s, and 2s in it, and what does 52 have? It's 2 and 26? So it has 2s and 13s in it. So 17 should be co-prime with this number, because I think the prime numbers of 3,120 are 2s, 3s, 5s, and 13s. I don't see any 17s in the factorization of these two numbers. So I think we should be okay. All right, so let's go ahead, let's select E is equal to 17. The last thing that we need is to find the inverse of E mod 3,120. So we need to find d times some number 17 is congruent to 1 mod 3,120. So we're on the hunt for this magical number d that's going to help us create the private key, right? D is the decrypting piece of this puzzle. So let's go ahead and use the Euclidean algorithm to find that value. What do we need to do here? I think we just need to take our large number and we start dividing by 17, right? So let's take 3,120. Let's assign that to our first value that we're working with. We'll take 17, we'll assign that to the second value that we're working with, and then we'll start doing some subtraction. I'm just going to pull up the calculator here. So 3,120. I need to divide this by 17 and see how many times 17 goes into this number. So it looks like it's going to be 183. Ooh, yuck. Okay. So we are going to take R1 and we're going to subtract 183 copies of R2. Let's see what we're left over with when we do that. So 3,120, let's subtract off 183 copies of 17. That's going to leave us with the number 9. Okay, looking at column 2, we have 1, take away 0, so we're going to be left with 1. And then looking at column 3, we're going to have 0, take away 183. So I'll have negative 183 here in column 3. Now we're going to go ahead and compare our next two values, 17 and 9. That's going to be just 1, right? So we're going to be able to get 1, 9 in there, and we're going to be left over with, what, 8. So let's take row, let's go black. Row 2, and we'll take away a copy of row 3. And we know 17 take away 9 should be 8. We have 0 take away 1, and then 1 plus 183 will give us 184. Yeah, it's a Bézier problem. Yeah, exactly. Bézier's algorithm, yeah.
There are many flavors. Subtraction,
or Bézier's
division, ARBQR, binary, shifts, continued fraction, matrix with unimodular steps, D*Plotfus 1. All keep GCD, extended tracks, Bézier XY.
And then our final step here is just going to be comparing these two. We know that we can take, what is this, row 3. Let's subtract 1 copy of row 4. 9 take away 8 is 1. 1 plus 1 is 2. And then we have negative 183 take away 184 more. That's going to be big. Okay, clear. So let's take negative 183, take away another 184. So we get negative 367. Now, obviously, if we were to continue this one more round, we'd have row 4 minus 8, row 5. That's going to give us the 0 here that we would need to complete or finish off the Euclidean algorithm. So we're going to go ahead and stop here. And the information that we need is sitting here right in this particular row. So what we get from this is we get that 1 is equivalent to 2 copies of 3,120 and subtract 367 copies of 17. Okay, so we were able to express the GCD of these two numbers, which we know is 1, as a linear combination of 3120 and 17. Now, how does this help us with the original problem? I just have to think about this for a hot second. We need, I guess, to take everything mod 3120 is what we want, right? So if I take this and I apply mod 3120 to it, what do we get? So let's apply mod 3120. That's going to give us 1. Mod 3120 is equivalent to, we'll get 0 here for this first term. That's going to disappear. And then we'll get minus 367 times 17. So in other words, we know that negative 367 times 17 is congruent to 1 mod 3120. So this is the inverse that we want. It's just not in a form that's super helpful for us. We would probably prefer this to be the smallest positive congruence class. But this is the D that we're looking for. Now let's just turn it into the smallest positive congruence class. Now we should be able to do this, I think, relatively straightforward by just adding 3,120 to it. That should pop it up into the positive region, and that way we're going to have a decryption value that's somewhere between 1 and the phi of n that we're working with. So let's go ahead and do that. So we're going to say, therefore, D is going to be negative 367. We're going to add the 3120 to it just to pop it up into a congruence class that will be a little bit easier for us for calculations. So negative 367, we're going to add 3120. And we get 2,753. All right, so we have our two pieces of information. We have our public key, which is n, so 3,233, and then the encryption number, which was 17. And then we have our private key, which is 3,233, as well as our decryption number, which is 2,753. Okay, let's move into step 2. So now that we have the initialization phase, we know what the public and the private key look like, we'll go and start moving into the encryption phase. So the idea now is we can go ahead and send that public key to the server. That's going to begin the encryption process. And for the sake of just making things relatively straightforward, I'm just going to use ASCII here. I'm sure that those of you that maybe have a bit more experience with cryptographic algorithms, maybe there's something else used. I think I wrote down here UTF-8. I don't really know exactly what is used in theory and practice. For me, ASCII was relatively straightforward to use, so that's what I use to do my encryption. So we got to think about this in one of two ways. Either whatever the plain text message is after we convert it into some kind of numerical string, either that string has to be less than n, or we have to reasonably divvy it up in a way that makes sense. So if the plain text message is smaller than the n that we choose, cool, we can just do it all in one go. If the plain text message is bigger than the n that we choose, then what we probably want to do is divvy that up maybe character by character or in some other kind of way that makes sense. I almost said smaller bits, but that I shouldn't write that. Let's just say smaller pieces. Okay, once we have divided up the plain text message in a way that makes sense for us, we'll go ahead and we'll encrypt the message by doing the following calculation. So our ciphertext, which is capital C, is going to be p to the power of the encoding key, or the encoding number, mod n. So let's see how this might be reasonably done using ASCII. So let's say we want to send a plain text message hello to somebody. Keep it nice and simple for this particular example because there are some computations that you might want to do. Okay, so suppose our plain text message is hello. All capital letters. If I were to take hello and convert that into ASCII, I would get 7269767679. So if I were to combine all of these numbers together, I would get something that's larger than the mod that we're working with in our particular example, which was what, like 3233, I think. So I've gone ahead and I've decided I'm going to break this up and go character by character. So I'm going to label each character as like PI. I'm going to say the first character is 72, second character is 69, and so on and so on. P3, P4 are the same. They're both 76, are L's. And then O is 79. And then what we want to do is take these numbers, raise it to the power of 17 because that's our encryption number, 17, and then calculate that mod 3,233. So I'm just going to go ahead and maybe do that up here. So we want to take 72 to the 17, mod 3233. So I'll go ahead and write all these out. Now you can use R if you want to do some of this work. You can use an online calculator if we're working with small enough numbers here. Choice is yours, totally fine either way. Why am I writing 12, 17? I'll go ahead and just kind of jot in the values that I got when I did these calculations. So for 72 to the 17, and when I take that mod 3233, I get 3000. So that becomes the first part of our cipher text message. Okay, that particular 4-digit number. The second value came out as 28. The next two values came out as 27, 26. And then for P5, we got 1307. So you might just want to double check and make sure you can get those values using some kind of online calculator, LLM tool, or one of your programs like R or Python. So these become our 5 ciphertext pieces that we're going to be basically sending back to the individual that has requested that information. And that's all there is to the encryption step. So let's talk about step 3, which is kind of like the step where the magic happens. That's the decryption step. So all that encryption happened with only the public key. So only the number 17 and our 3233. When this information comes back to the individual, or back to kind of where the client side is, we have the inverse, which is, what do we say, like 27 something? What was it? 2,753. So we have the inverse of 17, mod phi n, but maybe it's not super obvious why this particular number is going to help us decrypt these values that we got, right? So how does that all kind of connect together? And my claim is that if I take a piece of that ciphertext and I raise it to the power of D, and I take that mod n, that should return back the plain text message, right? So of course ours was divvied up into 5 different pieces, so we would put each of those 5 pieces into this formula, and we should be able to get out the 5 numbers in ASCII code for the word hello. And let's see if I can get this logic correct, because this is really kind of cool. So let's consider this. I'm just going to write this in red. So let's consider let's say I have the plain text message and I raise that to the power of e, so I've kind of encoded the plain text message. If I now take that to the power of d, or decode that, I should get back to the plain text message, right? That's kind of the idea, right? If I encode it and then go through the process of decoding it, mod n in this case, I should get back to the original plain text message. So we're going to kind of consider this setup, and we're basically going to say the following. We're going to say if we're okay that e times d, or d times e, is congruent to 1 mod phi of n, right? So if multiplying these two things together is congruent to 1, so if these two things are indeed inverses of each other, then we could say that e times d is equal to 1 plus some multiple of phi n. Right, so these two things should be the same. And in fact, we saw that earlier, right, when we were working on our example. We can even scroll back and take a little peek-see-poo at that. Right? It's actually right here. No, I apologize. That's the modulo equation. It's actually right here in red. Right, so we were able to express 1 as a linear combination of 3120, which was our phi n, and 17 and its inverse. Right, so that's all we're saying here. We're saying, well, we should be able to write 17 and its inverse as 1, maybe plus some multiple, some unknown multiple of phi of n. In our case, we know what that multiple is. It's 2. So that's all I'm saying down here. I should be able to rewrite this in the following way. So if that's true, and maybe I'll put some stipulations on k here. Maybe we could just say that k is some integer, right? So if that's true, then p to the e to the d is really just p to the e times d. But we've said that we can think about that as p to the 1 plus some multiple of phi of n. Now the 1 plus k phi of n is all in the power, so now we can actually think about this as multiplication. So we get p times p to the k times phi n. Right, so just kind of using our power laws to break this apart. And we could even go one step further if we wanted to. Let's see, is it important? Yeah, it looks important in my notes here. So we could even say this is p times p phi of n all to the power of k. Okay, so there's a little bit of work involved here, and it really relies on the fact that e and d are inverses of each other, mod phi n. So if they're inverses of each other, mod phi n, which is what we stipulated above, then I have this kind of relationship. When I apply mod n, look what happens. We get that p times p phi of n to the k will be congruent to, I'm going to claim p times 1 to the k mod n. Now that seems like some mathemagics. What in the world is happening? What allows us to basically say that this must be equivalent to 1? How does that work? Mod n. Well, we saw this really lovely theorem in our modular arithmetic section called Euler's theorem. And Euler's theorem says, if n and a are coprime, then a to the phi of n is congruent to 1 mod n. So we're using that kind of tricky piece here. So we're basically saying, okay, if, in our case, if p and phi of n are coprime, then this should be equivalent to 1, right? So the idea is if this is true, if this p to the phi of n to the k is really 1 to the k, then we get that this is all really congruent to p mod n. Okay, so we can recapture the plain text message by first encrypting it and then decrypting it. We get back to the original message. So kind of cool. So there you go. There's kind of the theoretical underpinnings about why it works. Let's look at the example and just try to finish off that example and kind of tie everything back together. Okay, so we were working with the following ciphertext message. We had 3000, so our C was equal to 3028. You say you have so many streams open at once. How many streams do you have open at once? And 1307. All right, so the last step is basically to take our ciphertext message. We have already divided it up into 5 different slices. We've called them C1, C2, C3, C4, and C5. And we just got to convert them back into plain text messages. So plain text message 1 is just C1 to the power of D mod n. So I'll write out the first one, 3000. Our decryption number was 2753. So this is where we might need a little bit of online help, or we might need to use our Python to do some of this work for us, because we have some pretty intensive calculations. Like my calculator definitely cannot do this. But you may want to verify that this indeed does come back out to 72, which will convert back into the H that we're looking for when we go from ASCII back to letters and numbers. Okay, so our P2 calculated similarly. We'll take our 28, raise it to the 2753, take that mod 3233, and that should come out to be the 69 we were looking for, and so on. P3 and P4 are the same, right? So we can just do one calculation here. Yeah, that's fine. These should both come out to be 76. And then we have P5, which is 1307 to the 2753 mod. 3233. That's going to pop out to be our original 79 that we were looking for. And then the idea is to collect these back up. That becomes our plain text message, and then we convert that back to our letters. So our plain text message, what was it, 72 I think we started with, right? So 72, 69, 76, 76, 79. Now we want to convert that back into hello. All right, we're almost done here. We're just going to talk a little bit about advantages and disadvantages. And we'll make some comparisons back to the Diffie-Hellman key exchange as well. And that'll tie up everything in the video that we want to talk about today. So RSA is used for things like digital signatures, password exchanges, online banking. And online shopping. RSA is suitable for real-time applications, although it says here that the algorithm's slightly slower than others when we're working with a large amount of data. So with regards to a lot of these algorithms, I think for RSA, there's kind of like give and take between kind of what we need computationally to make things work and the amount of security it offers. So I think what RSA provides, it kind of like skips a little bit on the security side in exchange for requiring a little bit more space to do its work. That's kind of the gist that I got from the source that I was looking at. And that has something to do with the key sizes. We're using really, really big prime numbers. So when we go to actually calculate these public and private keys, those values tend to be quite large and take up quite a few... it takes up a lot of bits, I believe, with regards to these key sizes. There are a couple of vulnerabilities. So I wrote down one here that I think is interesting. If two public keys are known, so if two public keys share similar prime numbers, I wrote down you might be able to calculate the GCD of PQ, which would be the first N, and then PR, which would be the second N that somebody else is using. So those are the two different public keys. Maybe I'll just write them in green here. So this is kind of like N1, and this would be N2. So if they're similar enough, or we start doing some comparisons, maybe it's possible to find the shared factor of these two n's. In which case we're like, oh, cool. Now I have the one of the two prime numbers that I need to kind of crack the code here. So if they could solve for p in one of these, then boom, it's really easy to get the other large prime number they're looking for, and then everything kind of falls apart and breaks. So that's one kind of possibility, or one vulnerability here. The other one that I had was that so this is kind of answering the first question I had, was what happens if P and Q aren't far enough away. So if P and Q are too close, then P, so the plain text message encoded, would be less than N. Oh, okay. So this could be the case, or the private key, so or private key D is too small. So if that happens, I guess it's probably computationally easy to calculate what that private key should be. So Megalomorph is adding just a little bit of kind of extra commentary to this first vulnerability, which I think is important. Yeah, you're right. It's not necessarily that they're similar prime numbers. It's actually that they share a prime number, right? So if two public keys share a prime number, then this GCD attack might be feasible. And so Megalomorph is saying, which is true, like we need a good random number generator to pick those prime numbers. Yeah. I think that in practice you just generate large numbers and check to see if they're strong pseudo primes. Again, it's a little out of my wheelhouse. I haven't taken a cryptography course in quite some time. That could be the case. Strong pseudo primes is probably good enough. Yeah. So asymmetric encryption. We have basically a public and a private key. I need both. I give up my public key. Things get encoded or encrypted with the public key. Only the private key can unlock that information. That was terrible penmanship. After all of this talk about how nice my penmanship, that was terrible. Whereas something like Diffie-Hellman is a precursor to what we call symmetric encryption. And in symmetric encryption, there's one shared private key, one shared secret key. Okay, so that's the only key that is able to do all of the work, and DH creates that shared private key. So I think that's what I'm trying to say here. Okay, so that's one main difference. So I would assume here when I say generating keys for each RSA session, the idea here is that that initialization phase to create the keys probably takes a little bit more time for RSA because we're working with really, really large prime numbers here, and then values that are also going to be quite large when we're working computationally. It feels like it's probably a bit easier, a bit quicker for Diffie-Hellman. So this is an interesting point. Let's kind of just talk about this for a second. So RSA provides no forward security. So what does that mean? It means that so I wrote down a leaked RSA key. So let's say you were able to find somebody's private key. So a leaked private key would decrypt all past and future messages. Yeah, that's true, right? So in light of the last point, if it doesn't make sense for us to just like go through the RSA procedure a bunch of times every session, we probably have a lot of static sessions, right? Or a single static session that generates the keys. So if we were to accidentally misplace our private key, then everything that we've encrypted in the past and everything we're going to encrypt in the future is all seen by the attacker. Yeah, that makes sense. Okay, so that's what we mean by no forward security. And that's because the key is static. That's kind of the big idea here. So when we say key is static, that key, it doesn't change very often because it's probably computationally expensive to go through that all the time. So DH, on the other hand, so Diffie-Hellman key exchange, because it's a little bit faster or quicker to go through that initialization procedure, we have forward security because the DH procedure is going to update every time we go to do it. Right? So if my attacker finds a particular thing, they're only going to be able to undo maybe that thing because the key isn't static here. So if I accidentally misplace my shared secret key, oops, they can see that one particular message, but it gets updated in the next round of DH. So remember that RSA, its difficulty lies in the factoring of large numbers. Whereas DH's difficulty lies in solving really awkward mod arithmetic equations, I guess. Like a to the x congruent to b mod p. So yeah, so DH is set up to be this really tricky modular arithmetic problem. And something that was mentioned as we were kind of floating through the ether, RSA will authenticate and DH will not. So to my knowledge, kind of when I was reading and in kind of creating notes for the course, DH is typically coupled with some other algorithm that would do the authentication process. So there you go. That's going to complete a little bit of an introduction to what Diffie-Hellman key exchange and what RSA looks like, doing a little bit comparing and contrasting of those two things with a little bit of help from chat. Always much appreciated. If we do make some more videos for you, it's probably going to be on some of the more advanced stuff like FISTO networks. We might look a little bit at DES, AES, for example, and then we'll definitely want to look at some cryptographic hash functions because I think it's important to understand kind of roughly what those things do So I might take a look at the SHA algorithm or something like that in a future video as well. But until then, take care, guys. And that's going to finish off this video for you.